Hello everybody, my name is Mattia Fumagalli. I am from the Conceptual and Cognitive Modeling Research Group, University of Bolzano. The work I am going to present you is the result of a collaboration with Gabor Bella, Samuele Conti and Fausto Giunchiglia from the University of Trento. Before starting to present the paper, I would like to thank the people and organization at FOIS who gave us the opportunity to share the work. This work, was titled Ontology-Driven Cross-Domain Transfer Learning, goes back to 2 years ago. It was submitted at FOIS 2020. The structure of the presentation goes as follows. We firstly give a brief description of the context in which we put our proposal. We then briefly describe the mere related work addressing the same challenge we want to address. And after that, we describe our proposal. Lastly, we discuss some final remarks. While in the last decade statistical approaches and machine learning in AI have been vastly successful in solving complex tasks, most solutions proceed by learning standalone models from large amounts of raw or annotated data. A long-standing ambition of research in artificial intelligence, which can be considered as an open research issue, is then to achieve and exceed the human ability for generalization, possibly by decreasing the number of data needed to address a task, and enabling the reuse of learned models across domains of application. Now, suppose we have an image recognition task, where the goal is to recognize two animals, for instance cats and lynxes. Suppose we train a model with thousands of samples about cats. The model will be able to correctly identify, with high level of accuracy, only cats. On the other side, humans could easily recognize both those animals by just having few encounters with cats and having a simple description of what is a lynx. The limitation of traditional machine learning methods compared to the human generalization ability is due to two common assumptions. Firstly, the target data domain, what we call here test set, and the source data domain, what we call here training set, must be the same. Here, in this context, a domain is taken as a tuple phi and p of x, with phi being a feature space and with p of x being a marginal probability distribution. The second assumption is that the target and the source tasks are the same. Here, a task is taken as a tuple with y and f, with y being a label space, and with f being a predictive function that can be learned from the training data, which consists of pairs x and y, where x is a record in the dataset and y is a label assigned to that record. For instance, considering the cat-lynx example, the source and target label spaces will be the same if they both contain cat and lynx as labels. In this context, transfer learning has been the research area that tries to simulate generalization by applying learned models to new tasks. Transfer learning can be defined as follows. Given a source domain and a source learning task, a target domain and a target learning task, transfer learning aims to help improving the learning of the target predictive function in the target domain, using the knowledge in the source domain and source task, where the source domain is different from the target task, or the target task is different from the source task. With transfer learning at test time, a learner observes samples from classes that were not observed during training, and needs to predict the class they belong to. For instance, how can we recognize lynxes if we have trained our model with images about cats only? Transfer learning tries exactly to address this issue. So, we could say that the common goal of the vast range of transfer learning techniques, as for instance zero-shot learning, is knowledge reuse, namely associating observed and non-observed objects through some form of auxiliary information, which encodes observable distinguishing properties of the objects. Now, to better understand the solution we propose in this paper, let's first take this graph as a representation of what we call here traditional machine learning setup, where the blue node is the image with a lynx and a cat. Light gray nodes are the classes observed only during training, for instance, classes of cats, while nodes are never observed but must be inferred, for instance, classes of links. In this traditional setup, a multi-class classifier learns one parameter, alpha, for each training class and cannot generalize to classes Z that are not part of the training set. Now, let's take this new graph. This can be taken as a knowledge-enhanced attribute-based classifier. Here, the knowledge is encoded as a schema where class-attribute relations are fixed. See the thick lines in the represented graph. For instance, suppose we have small, large, big ears, brown as attributes A, and the knowledge encodes that lynxes are large, brown, with big ears, and cats are small and can have multiple colors. In this setting, we can train the attribute classifier just using pictures about cats, and saying, for instance, if a cat is brown, if it has big ears, and so forth. Namely, training labels Y imply training values for the attributes A. From here, parameters beta are learned. Attribute values can be then directly inferred in a second step. This implying the capability of identifying output classes, even for previously unseen classes, like lynxes. Current approaches adopt flat lists of attributes and related classes, usually extracting information from vocabularies and text. This is good to collect a lot of information and attributes, but does not imply a clear-cut distinction between classes. Namely, classes are not necessarily well defined. For instance, a cat and dog may just be defined as having a head, ear, and snout. Moreover, in the current approaches, no class hierarchy is provided. Thus, no more general classes can be inferred, and no properties can be inferred by more general classes. The core idea underlying our paper is that the knowledge structure used in this setup, when properly organized according to ontological principles, provides two major tools for cross-domain transfer, namely generalization and discrimination. While generalization uncovers the overlap between the semantic spaces across domains, discrimination provides distinctive properties of classes as key features to the transfer learning process. The hypothesis we tested in this paper is that these two tools can improve the performance of the task involved with the transfer of knowledge. Here, we provide an overview of the architecture we implemented. First, we extract basic features from images, about observed animals like cats. These features are about pixels, shapes, and so forth. Basically, they are low-level features as from state-of-the-art feature extraction approaches. Second, we train property predictors, namely binomial classifiers, over the extracted features, where each property predictor is associated to a property that, in turn, is associated to a class provided by an input ontology. Then, we give a set of images with also not observed animals, like lynxes for instance, to the feature extractor. We use the output features as test of the property predictors. The property predictors generate an output where each input image is associated to a set of properties with some weights. Finally, we use the ontological knowledge for classifying all the results with a hierarchical classification algorithm. We evaluated our approach as follows. We reused and extended the Pascal Yahoo dataset and annotations, which is a popular dataset for image classification tasks. Then we manually sampled this dataset for over 12,000 images relating to two domains. The first domain is the household domain with 7,490 images, about everyday objects around the house. The second domain was the travel domain with 5,203 images about holidays and travel-related objects. The training images were part of the household domain. The test images were from the travel domain. As part of cross-domain transfer, we evaluated both cross-task performance with the prediction of unseen classes, namely not used in training, and same task performance, where the same classes are predicted across domains. For instance, a class like car was present in both domains. The evaluations covered three types of knowledge. Firstly, a state-of-the-art flat classifier covering basic classes structured according to previous work, containing classes like person, car, bird, bottle, associated to some attributes. Second, a domain ontology classifier, where we introduced domain ontological knowledge. Thirdly, a domain plus top-level classifier, where we introduced some top-level concept and top-level properties, covering all the concept of both domains. While we are careful not to draw overly general conclusions from experimenting with a single set of ontologies, we still observe a few salient phenomena. Table 1 reports global accuracy results across the entire test dataset. For the three setups we presented above, and on the three class levels, namely top-level classes, mid-level classes, and base classes. Running some quick observations, we may see that on base classes a major difference is observed for the domain ontology-based setup with respect to the state-of-the-art flat classifier. This improvement was due to the discriminative properties introduced by the domain ontology classifier. The positive effect of the top-level ontology is then more obvious on the top and mid-level classes, where the top-level ontology, by introducing more general classes, is clearly enabling high precision and high recall prediction for cross-domain concepts. For more details about their architecture and evaluation, please check the full version of the paper, where links to process and data are also provided. As final remarks, here are some key activities that we put in the agenda for the immediate future work. For instance, using and comparing existing top-level ontologies in the current setup, addressing new domains and testing available domain ontologies, assessing other available machine learning algorithms to improve the performance of the task, exploring the approach over different input data, text, audio, or others. Thank you a lot for your attention. We are really looking forward for your feedback, questions, and suggestions.